So we have already talked about filtering in terms of linear filters, and I would now like to continue with nonlinear filters. So the idea of nonlinear filters is nonlinear filters are against overvoltages or are against surge signals that are high in amplitude and that have therefore short duration and high amplitude. And if something is short in time, how does the spectrum of such signals look like? If you remember what we talked about, time domain and frequency domain. If some signals are short in time, have a short rise time, a short fall time, pulse signals like a lightning strike, like some electrostatic discharge pulse. How does the spectrum of these signals look like? It's rather broad in frequency. So if we have a short pulse, a transient disturbance, a linear filter will not help us because such disturbance signals have a broad spectrum, and so you would need to filter almost all frequency components, and then you will probably also filter your useful signal. If you have a broadband disturbance, linear filters will not really work. Yeah, so with these nonlinear filters, we want to reduce transient interference signals. And so there are different types of this that we will look in more detail in a second: diodes, Zener diodes, Thyristors, and so on. And the problem is, as already discussed now, that there is some overlap of the spectrum of the wanted signal and the unwanted signal. So our useful signal might have, or usually has, a limited frequency range. If you transmit a clock signal somewhere, if you transmit data, you have some channel where you transmit. And if you have short transient pulses, short transient disturbances, they have a broad spectrum, so they will overlap with your useful signal. And that's why you cannot filter out this green marked unwanted signal here with some linear filter, because then you will also filter your useful signal. Yeah, if the unwanted interference would also look like this, okay, then we could have a low pass filter, let our useful signal go through, filter away the high frequency component, or if the unwanted signal would be here somewhere, and then we would use a high pass filter, let our useful signal get through, block the low frequency disturbance signal. But in this case, linear filter does not work. Okay, so we somehow still need to get rid of this high voltage, high current, high power, maybe transient interference. And the idea is by just blocking it. So we need some attenuation of disturbance, and still the useful transient response characteristic of our signal should not be disturbed. And if we want to dissipate this energy, the blocking device that we use, like a diode, of course, it must be able to dissipate this current. Yeah, so if we have some protection device, the energy of the interference should not destroy this element. So this is, these are the demands for getting rid of the disturbance, and the demands for the transmission still of our wanted signal here is that the wanted signal, of course, should not be disturbed. So there should be low attenuation, there should be low reflection of the wanted signal, and intermodulation means that no additional frequency components should be generated from our wanted signal. Which can happen because a nonlinear filter, as the name nonlinear says, consists of nonlinear components. And so nonlinear components could also create additional frequencies. So you have this useful signal band, and you feed it to some nonlinear components, and then harmonics would be generated. So from this useful signal, you might generate a first harmonic, a second harmonic, and so on in a higher frequency edge, then that might disturb something else. And this, of course, should also not happen. This is meant with intermodulation. No generation of harmonics, something like this. Okay, so now we can have a look at what types of nonlinear protective circuit components we have. And the first one is we use diodes. And the advantage of diodes is diodes are simple, and diodes can be also directly placed, for example, on the silicon wafer of some chip. And so the disadvantage with diodes is they cannot, at least if you put them on a chip, they cannot carry a high current. But their response time is very short because they are so small. They have some internal resistance that somehow limits the current, and they fix the voltage to a typical value like 0.7 for silicon diodes, and for germanium diodes it's a little less. And so because you can put them directly on a chip, they are often used for electrostatic discharge protection directly on a chip. So there the challenge is you can put them directly on a chip if they should have or if they need to have a high current carrying capacity. So if they should be able to dissipate a high current, then you need to have a large area on the chip. And then this, of course, somehow costs money because it will consume more space on the chip. So there's some trade-off that you usually need to do. But this putting diodes against ESD directly on a chip is usually a good countermeasure against ESD. And every chip that you buy somewhere, every chip that is manufactured will have some kind of internal ESD protection, at least against the electrostatic discharge that might happen during the fabrication process. If you manipulate the wafers in the fab, there's also triboelectricity, not very large, but still this could destroy the chip already in the production process. So at the ports or at points where you handle the chip, there is some kind of ESD protection already built in there. Okay, so then the question that might be discussed here is how does, and let me copy this to paste it into a drawing program. So how does this, and here's already the picture open from the linear filter, how does this circuit work? Or what does the circuit do? So this would be our supply voltage here, and for a chip, I don't know, it might be something like 3.3 volts. And this is the input. And on the other side, we have the output of this nonlinear filter. And now we have these two diodes. And how would a diode in this way or in this direction work?
With a negative signal?
Say again?
Like with a negative signal?
Yeah, with a negative signal, exactly. So a diode like this can only conduct a current in this direction. And if it's conducting a current in this direction, then this voltage drop would be approximately the 0.7 volts. And so we can have no larger voltages in this direction. So the voltage in this direction will always be smaller. Maybe I will draw it like this. The voltage in this direction will always be smaller as 0.7 volts. And so if our input voltage is smaller. Oh, maybe let me take a different color for this, maybe green. So this diode can only carry a current in this direction, and then this voltage here will be always smaller and equal to 0.7 volts. So this means if the input voltage, for example, is 0 volts, okay, nothing happens. We have no difference between here and between the ground, no problem. But if the voltage here gets smaller, if the input voltage, right, this would be our input voltage, if the input voltage U in is smaller than minus 0.7 volt, then this diode would get conducting and there would be a current flowing through this diode from the ground to increase this voltage and increase this voltage so much that it's not below this threshold anymore. So with this diode we can limit, or this diode will get conducting if our input voltage drops below the 0.7 volt. So this will make sure, let's say at the end, the outcome is that U1 is always greater than 0.7 volt due to this diode. Okay, and if I take a different color for this top diode, the top diode, of course, can also only carry a current in the upward direction. So in this case, the voltage drop in this direction will also be limited to the 0.7 volt. And so if our input voltage gets larger than the supply voltage minus the 0.7, right? Then this diode will get if the input voltage, so what happens here is if our input voltage U in is greater than the 3.3 or greater or equal than the 3.3 plus 0.7 volt, then this diode will get conducting, and every voltage that, or charges and current and so on from this voltage that is higher than this will go to the supply voltage of our circuit, and don't do any harm there. So this means that the input voltage will always be smaller at the end than the 3.3 volts plus 0.7 volts, the forward voltage of the diode. So at the end, the outcome of this circuit is that our input voltage, and therefore also the output voltage, because at the end they are at the same potential here, that the input and the output voltage will be larger or equal than 0 volt, let's say our ground voltage, our ground potential minus the 0.7 volts, and they will be always smaller than the supply voltage, 3.3 volts plus the 0.7 volts. That's the outcome of this filter, of this nonlinear filter. So the diodes somehow clip this voltage, limit this voltage to this range. And this range ground potential minus a little bit, supply voltage plus a little bit, this will usually not do any harm to the circuit that follows. And the resistance here is a little bit to decouple the input from the output, but the resistance, of course, also introduces some additional attenuation into the circuit. Okay, so then the same thing can be done with Zener diodes. These Zener diodes or Zener diodes are diodes that you would usually use in the reverse direction. So in the forward direction they behave like usual diodes, and in the reverse direction they also behave like diodes. They get conducting above a certain voltage, but the certain voltage is the so-called Zener voltage, and it depends on how you build up the diode, and it can be something like 10 volts, can be 50 volts, can be 5 volts, something like this. And so with Zener diodes you can use a circuit that looks like this with two diodes in an anti-series connection. And yeah, so if we would take a look at how this circuit works, if I copy this, paste it into a drawing program, and if we once again take a look at, this is our input voltage U1, and so if this input voltage is very high, if the input voltage is much larger, let's say, than the Zener voltage of one of these diodes, then yeah, so we will have a current going in this way. So the voltage drop across this diode, so here this diode will be just conducting in this case, we will have the 0.7 volt there, and so here we will have this Zener voltage. Yeah, so if our input voltage is larger than the Zener voltage plus the conducting forward voltage of the second diode, let's say 0.7 volt, then it will be conducting in this state. And so in the second case, if the input voltage is smaller than Zener voltage minus, no, also plus 0.7 volt, we will check in a second. Yeah, so if the input voltage has the same but in the opposite direction, yeah, so then we will have the 0.7 volt here, because this diode will be conducting, current will go in this direction. Yeah, the current will be fed from the ground node, and we will have the Zener voltage across this diode. So, and I think then we need to have some minus here to account for the direction. So this type of protective circuit, if we do the same comparison as before, will limit our input voltage U in, and therefore, let's say also more or less the output voltage, except for the voltage drop across this resistor here, to this range that the voltage will be always larger than minus Zener voltage plus 0.7 volt, and it will be always smaller than Zener voltage plus 0.7 volt. So here it's kind of symmetrical around ground potential, and in this case it was kind of ground potential minus something, supply voltage plus something. Yeah, but with this Zener diodes, we have no reference to our supply voltage here. We just limit it, let's say, to our signal voltage plus plus and minus symmetrical to the Zener voltage, let's say. Okay, so this is what happens here. This is this Clarence Zener guy after these diodes are named. He was some American engineer and physicist that made this invention and findings in the 1940s and 50s and 60s. So then another nonlinear protective circuit would be a thyristor or triac. There the thing is, you need to ignite them first. Yeah, so there's an overvoltage, it will ignite the circuit, and then this triac, for example, becomes conductive and can protect the circuit. So usually there's also some kind of series resistor or series resistance to induct, to limit the current. There might be some inductor, or at least also some parasitic series inductance in this circuit. And another issue is that these thyristors have to be turned off. And if your disturbance current does not fall below a certain threshold, then it might not turn off. So for example, if the desired signal, you have some signal and there's just a small disturbance, it will trigger this device, and then it will get conductive, it will protect the circuit, but it will not switch off anymore. This can be a problem. And so another issue is that this ignition takes some time, so the response time is, let's say, just in the microseconds range. So usually you would need to combine such thyristor or triac with another protective element that reacts faster, like a diode that we said before. Diodes react in the nanosecond range. This takes some orders of magnitude longer. So this is, let's say, some more heavy protection maybe for supply lines, something like this. And then the circuit would look like this. So you have a fast fuse. You have some inductor, so to somehow limit high frequency components. So if you have a fast disturbance, so this is, let's say, like as we said, like a low pass filter. And so your fast disturbance, the high frequency components of the disturbance, they cannot directly pass this inductor, and so they will then ignite the thyristor. And so this will get conductive, and this will then dissipate the disturbance current of some switching pulse, of some lightning strike, of some surge pulse, something like this. And so then another thing that works in the same way is you take a spark gap inside a gas-filled surge arrestor. So there's some component in a glass housing, there are just two electrodes, and if the voltage difference, or the potential difference, if the voltage between these two electrodes gets too high, then this element will get conductive, and it will also dissipate the disturbance current against ground. And so inside this gas-filled surge arrestor, then you will have a small lightning, or there will be some ionization, and this has some certain resistance. So usually no additional series resistor is required for current limitation. And also, this might not turn off. Right, once the gas inside there is ionized, it might stay conductive, and so if the voltage does not drop below a certain threshold, this flash, this spark will just continue to exist. Yeah, so this also needs to be combined, let's say, for example, with some fuse, and then the fuse will switch it off. And yeah, but of course, if the fuse switches it off, then it will only work one time. Yeah, so it's a protective against, let's say, you have there's a chance that a certain device, a certain instrument, a certain installation is maybe hit by lightning every 1 or 2 years, and if it is hit by lightning, and okay, this gas-filled surge arrestor will protect the device, still the fuse will be broken and someone needs to go there and replace the fuse. And otherwise the device will probably not work anymore, or the protection is not effective anymore. Yeah, so ignition voltages in this case are, as you can see, in a rather high voltage range up to some kilovolts, and then the voltage of this arc that is burning inside there is just some tens of volts. There is some parasitic capacitance that is very small, just some picofarads, so the disturbance of wanted signals is very small, but it also needs to be combined with some faster acting devices because the response time is not so great. It's also in the microsecond range. And the typical circuit symbol for such a gas-filled surge arrestor looks like this resistor-like symbol with some arrow in there for this. Yeah, for one of these electrodes, and where you have the arc or the spark gap. And the last protective element that we can take a look at is a varistor. And the varistor has a certain characteristic that, yeah, a little bit like a diode, is also some exponential function. Right? And for the diode, the exponential function is for the, yeah, inside this Schottky equation, and if you take the, let's say, the reciprocal function, it's some logarithmic function, and so that's why here it's written in a way of this logarithmic function. So current and voltage somehow have some logarithmic or also exponential relationship, and yeah, there are some factors in there, and one depends more on the geometry and one is some nonlinearity exponent. But what happens at the end is, if I go back to one drawing program, if we yeah, if you would take a look at the characteristic curve of some varistor, so if this is, for example, the voltage axis, and if this is the current axis, then the current voltage characteristic of some typical varistor, yeah, so this is here this varistor symbol, this is voltage, this is current, looks like, as said, a little bit like for a diode, that if you have small voltages, you have no current, almost no current, but from a certain voltage it gets conductive and you can have a very high current flow. And a diode would just look like this, right? No current flow in the opposite direction. But for a varistor, it's symmetrical, so it shows the same behavior also in the other direction. And yeah, the voltage here from where this varistor gets conductive, this depends, but is usually in the range of, let's say, some tens to 100 volt, depending on what type of varistor this is. And yeah, so one advantage of them is they're quite small and quite simple, and they also kind of react very fast. Yeah, and it's a little bit, the behavior is a little bit like the one of these two anti-series Zener diodes that we looked at before. So, and the characteristic of this circuit here, of this circuit, would be fairly similar to what we have just drawn here from this varistor. Yeah, and so once again, here you can see the symbol. Switching voltages here, there might be devices that also go up into the kilovolt range. I think it's difficult to have something below 7 volts due to the properties or characteristics of the semiconductor material. And as said, response time is usually rather fast. And so the idea for the protection of usual devices is that we have these different protection elements that we just discussed: diodes, Zener diodes, Thyristors, gas-filled surge arrestors, and this Varistors, and they all have their advantages and disadvantages, right? Some are reacting faster, but they cannot carry a high current. Some will only work for the low voltage range, some work for the high voltage range. Some are not that fast, but then they can carry a higher current and so on, that you somehow combine them in a way to use their advantages and to get rid of the disadvantages. And so a usual multi-stage protection circuit then might look like this, that you have a primary protection, right? And the primary protection could be, for example, this gas-filled surge arrestor that takes some time to respond, but once it responds, then it can dissipate a high current and it will really protect the device. So the problem is that this needs some time to react. So until this reacts, you have some overvoltage, you might have some overvoltage. Yeah, so you need to have some fine protection, like diodes, Zener diodes, varistor, that reacts faster, but that cannot carry such a high current, or that cannot dissipate so much energy. So this reacts slow, but can carry high current, can dissipate high energy. This reacts fast, but cannot dissipate so much energy. Then you take some resistance, inductance, some kind of, let's say, low-pass filter in between. Yeah, that, of course, this should not disturb and attenuate your useful signals too much. But then if you now have some rather large disturbance coming from this side, okay, it will propagate in this direction. At some certain time, this will get active, and this will get rid of the disturbance, and the portion that went through, this will then go into the fine protection. And before the fine protection gets destroyed with too much current and too much energy, this will have become active and will then dissipate the remaining part of the energy. Yeah, so you could, if I copy this and have a last schematic. So some new node here. So if I maybe move it to this side or somewhere to the center, so if our input voltage here looks like this over time, So this is the time and this is our input voltage. And let's say we have some very high voltage signal, some typical transient disturbance signal. So high voltage spike and then it somehow goes down. This would be some usual kind of double exponential pulse, lightning, waveform, surge waveform, something like this. So quite short rise time, some pulse width, and then some quite, in comparison, quite slow fall time. And so now this is what would happen here at our circuit. So then it would take some time until so now if we would take a look at the currents here and there in this circuit, so the current through our primary protection and the current through our fine protection. And if I draw these currents here in some schematic below this, so this is time and these are these two currents. So here's where the disturbance starts, but our primary protection needs some time to react. So unfortunately, nothing will happen at the beginning, but then it protects, and then it will. So the current will increase, and it will dissipate this current, and that we have there from our voltage, and everything will be fine. So if we take a look at the voltage that we have here at the fine protection, maybe let's say here at this decoupling point here in between. So at the beginning, our primary protection is not active, so we get some voltage, but then it's getting active, and then this voltage will drastically go down. So, but still you have some voltage spike here at the output, or you would get some voltage spike here at the output of the filter, but this is what we have the fine protection for. This is what we have this varistor for. And so if we take a look at the current through this varistor, then this will see the current at the beginning, and it will take over the current. And so then once this primary protection gets active, the fine protection, the secondary protection, does not need to be active anymore, and the current goes down. And so this reacts fast at the beginning, but cannot dissipate so much energy. And then after some time, this gets active, and this will dissipate the remaining energy. And so with this multi-stage protection, you can combine the advantages of both protective elements: fast response, high energy dissipating capacity, and you somehow get rid of the disadvantages. That's the idea of this multi-stage circuits. Okay, and so then we can have a very quick last look on active filters. If you want to build low-pass, high-pass filters from LCR components, if you would really like to go to low frequencies, if we go back to our transfer function that we had written down here, so if these corner frequencies should get low, it means we need really large capacitors, we need really large inductors. And if you want to have large capacitors for high voltage, then these capacitors get rather rather bulky, yeah, like this one here, just 0.22 microfarad, but for 1000 volt. And the same is for inductors. So if you want to have an inductor with some 100 micro, 1000 microhenry or millihenry range for some amperes, you get really large, heavy, bulky conductors. So the idea is to use active filters instead. This is some commercial product, for example, from TDK Epcos, and this series is called sine former, because the idea is you have a motor drive. The motor drive has some frequency converter, and the frequency converter, due to the power electronics, creates harmonics and consumes a non-sinusoidal current from the mains grid. And you want to get rid of these harmonics, you want to get a nice sinusoidal waveform, and that's why they call this sine former. And it works like this, that of course we still want to have some analog input and some analog output, but in between we take a low pass filter to do some sample and hold analog to digital conversion, and then we have some digital signal. So here we already have discrete time, here we have discrete amplitude. Then we do all the filtering in the digital stage, and there you are much more free to choose filter functions. You can have very sharp lobes and so on, and then you convert back into the analog domain using some digital to analog converter, have some additional smaller, simpler low-pass filter at the output, and have some analog output. And this is then, let's say, how these filters internally work. And of course, if the analog output is really some high current, high voltage signal, then behind this digital to analog converter, you need to have some amplifier, some kind of amplifier to really create currents and voltages that you need. But the advantage is that you don't need LNC in between. The behavior of LNC you do here in the digital domain. To still be able to generate a current, you need some amplifier at the output. But the amplifier at the output, once again, is power electronics. And so one idea is, of course, you could also, the behavior of the filter, already try to include into the power electronic circuits of the motor drive. That would be some idea there.